Hello, everybody. Today we're going to learn how to write a worm for GitHub Actions. This research was a result of about 3 months of work in which my goal was to find a new attack vector to attack CI/CD pipelines. Now, before we begin, how many of you use GitHub Actions by a raise of hand? Okay, I see a lot of people. Good. So it's relevant for you. Everybody else, maybe you'll learn about a new attack vector. So let me introduce myself. My name is Asi Greenholts. I'm a security researcher. I have about 8 years of experience in cybersecurity. For the last 3 years, I've been researching CI/CD security, first at Cybersecurity, which was later acquired by Palo Alto Networks. Here are some notable projects I've been a part of. So first one is the top 10 CI/CD security risks by OWASP. After that, we have the CI/CD GOAT, which is a deliberately vulnerable CI/CD environment if you want to learn how to attack CI/CD pipelines, and project I released a month ago, which is called Awesome CI/CD Attacks. You can also find it on GitHub. The best resources I've read about CI/CD offensive security in the last 3 years. Let's begin. So today we're going to learn how to build a GitHub Actions worm. In order to build a worm, we have few parts of the puzzle. Maybe at first everything won't seem related, but when we get to the worm itself, everything will eventually connect, and you'll learn how to write a GitHub Actions worm. So we're going to talk about initial attack vector, action dependencies, action to infect actions, how actions can infect other actions, and eventually we'll see how to find attack graphs at scale, and I'll show you some real cases from the real world. So let's begin by learning about initial attack vectors. So our first goal is to compromise a single GitHub repository, so we're able to maybe push code to the repository or abuse it somehow. Let's see one example of a known attack vector to compromise a GitHub repository that's called repojacking. So on the left, we have our repository, and it uses a dependency repository in the middle, which is part of an organization. When the developer, let's say, wakes up one day and decides to move the dependency repository to a new organization, GitHub automatically creates a redirect, and when we try to fetch the old name, it redirects us to the new name of the repository in the new GitHub organization. Now, let's say the developer decided to delete the old organization. Now, anyone can reclaim that name. And for example, a malicious attacker can create the old organization with the same name. What they can also do is create the same repository name. Next thing will happen when we'll try to fetch the repository again, the redirection will be canceled, and we will actually fetch a malicious repository. Now, GitHub knows this issue, and they've implemented a partial fix, let's say it. They retired the namespaces, basically organization names or usernames, of projects that had more than 100 clones in the week leading up to the owner's account being renamed or deleted. I won't get into the details, but this is still possible to exploit this attack for many reasons. Just keep notice of that and know that it's still possible to exploit this attack. Now, there are more known attack vectors. I've implemented in my research 3 more attack vectors that I've automated the discovery of. These are NPM email hijacking and GitHub Actions command injection. I won't get into the details, but just know they exist. You can later read on those attack vectors if you want. So we now know how to compromise a single repository, but how can we further our reach and get to more and more repositories? Basically, we want to write a worm, right? So let's talk about action dependencies, how actions are dependent on other actions. And in this part, our goal is to create a dependency tree of actions. Now, actions depend on other actions in 2 ways. The first way, before we get to the first way, let's learn a bit about what actions are. So actions are individual tasks that you can combine to create jobs and customize your workflows. Here you see a high-level architecture of GitHub Actions. Basically, you have some event that triggers a workflow. Workflow contains multiple jobs. Each job can contain multiple steps, and each step can contain an action or a script. So action is basically some code package you can write, and you can use it as modular parts of your pipeline to easily write pipelines, and you can also use actions that are written by the community. So if someone publishes a repository with an action, you can use it and you can find it on the GitHub marketplace, and you can directly find the repository itself, so everybody can share their code. Now let's talk about the dependency, the ways that actions depend on other actions. Here we have the action YAML file, which defines an action. Now, in the bottom of the file, we can see that this is action of type composite. We have other types of actions, but they're not relevant for this part. And composite actions can do two things. They can run other actions. They can also run scripts. In this example, we see that this action runs another action that's called actions checkout. So when someone runs the repository that this action YAML is inside, it runs the checkout action. So this is one dependency type. The other dependency type is through CI/CD. Actions also have their own GitHub Actions CI/CD workflows, and they probably use other actions in their CI/CD pipelines to build or test their code. In this example, we can see a few actions, but on the red box, you can see the setup node action, which sets up a node environment, which can then be used to install the project and test it, and so on. So what we can do is we can take both of these files, parse them, and if we parse the files and then do it recursively, basically parsing all the actions that depend on other actions and so on, we can create a beautiful tree of dependencies that looks like this. This beautiful flower of dependencies, you can see here on the purple nodes, you have repositories. Each repository is connected to orange nodes, which represent usage of an action inside a file. And each orange node is connected to a repository that hosts the action that's being used. So we have a recursion here that creates this beautiful actions dependency tree. Now, this is the same tree in a different representation. Let's say we have a target repository on the left that we want to attack. How can we do it? We have an initial action that we can try to compromise. Then we climb up the tree by infecting all the actions that are using it, basically creating a worm and affecting the target repository. How do we initially compromise the first repository? Using the initial attack vectors we talked about earlier, like repo jacking, npm, email hijacking, or command injection. That's it for this part. Next part is how do we do the actual infection in the chain? We need to climb up the tree. How can one action infect other actions? This part is more complicated, so I hope I won't lose you. So we need to learn a few things. We have here an example of a workflow file. You can see that we have two jobs, the first job and the second job. The first job has the first secret, the second job has the second secret. And also the second job has an interesting code here that what it does, it basically dumps the memory of the runner and grabs 4 secrets in memory, because in GitHub Actions, the secrets are stored in the memory in clear text. Now I know this thanks to a research done by Karim Rahal. You can see the link to the research below. And when we execute this code, we get the following decoded base64 text. We see here we have the second secret and the GitHub token. Now we don't see the first secret because, as I told you earlier, each job runs on a different runner. So we only have the second secret from the second job. And we have the GitHub token, which wasn't referenced at all in the file, but it still exists in the memory of the runner. So far we know that all secrets are accessible to all steps in a job, because the dumping of the memory was done before the secret was actually being used. And if you want to know why, you can read more in the research that I've referenced below. And another thing we know is that GitHub token is accessible even though it's not referenced at all. Now, what is the GitHub token? The GitHub token is a token generated at the start of each workflow, and it can be used by the workflow itself to communicate to the repository, to GitHub, and to perform actions on it. We can create pull requests, comment on pull requests, and one interesting thing, we can push code back to the repository if we have permissions. Now, what about permissions? So not too long ago, about a year ago, the default GitHub token permissions for repositories was read and write. GitHub changed it a year ago to be a default read, But all the repositories in the world that were created more than a year ago have a default write permission if it wasn't changed by anyone. Another thing we need to know is how to use actions. So to use actions, we have three ways. We can use a commit hash, a branch reference, and a git tag reference. Now, in our special case, we want to infect a repository by pushing malicious code to the repository, and we need to override a reference. We can't override a git commit hash because it's unique, but we can override a git tag, and we can push a new commit to a branch, basically to override the newest commit. Now, how the attack actually looks like is as follows. We have on the left our repository, an action repository, which has a CI/CD workflow that uses the compromised action using the main branch reference. When the workflow triggers, a GitHub token is being generated, and our compromised action can use it to push code back to the repository and infect the repository if it has the right permissions. Now, let's summarize what we know so far. This is the full attack, the whole story together, just so we understand before we see the real cases. So the first step is to compromise an initial action repository using one of the methods I've shown you earlier, like repojacking. The second step is to infect dependent repositories by pushing code back to the repositories when the actions or the compromised actions is being used. And the next step is just climbing up the tree and reaching our target repositories in which we can execute whatever code we want, we can steal secrets, we can modify its source code, and so on, maybe infecting more and more targets even outside of the GitHub platform. The next part, I'm going to show you how I found vulnerable attack graphs at scale on the internet, real cases. I used Neo4j database, as you've seen earlier, to create a huge graph. Later, after I created the huge graph of dependencies, I queried for a start of an attack node, initial attack node, and an end of the tree that ends in one of the target repositories I tried to attack. So the process was as follows. First, I collected targets. So I defined the 10K top repositories on GitHub. I also used ChaosDB, as you can see on the right, to create a list of 32K repositories of companies that have a bug bounty. Next thing I did was to filter out all the repositories that didn't use GitHub Actions. And then I cloned each repository. And then I checked for the 3 initial attack vectors automatically. If any one of them was possible, I connected an attack node to that repository. After that, I collected metadata about the action itself to see if it can actually propagate up the tree and infect other actions using it. So I collected if it has content write permissions. I was able to do that by parsing the log files of workflows in GitHub. They show you the permissions of the GitHub Actions token. Even in public repositories, you can see the permissions that are being used. It sounds simple. Turns out it's really complicated to actually gather this data efficiently and reliably, but eventually it worked. And I also collected what secrets are accessible by the action because I needed to collect all the secrets that are used in the same job that the action is using, because in addition to the GitHub token, the job might use a GitHub access token, which we can also use to infect a dependent repository if that access token has write permissions, and many other parameters you can see here in the image. And I did so recursively for everything. So I built this huge dependency tree of about, I think, 100,000 nodes, something like that. And here's an example from a real-world case that I've publicly disclosed, and they already fixed everything. So we'll use this case to understand the real impact of this attack. So on the right, we have us as the attacker, and I found the action zip repository, which is an action vulnerable to repojacking. So I claimed the organization. I'm now the owner of the old organization of this repository, and I validated that I can actually compromise the repository and repojack it. And this repository is being used by 2 other repositories, Hangfire repository, which is a very popular open source, and Veracode repository, which has a very long name. It's another action by Veracode. So I can see that by compromising the action zip repository, I can compromise 2 other repositories. Now that's not enough. Getting times 2 vulnerable repositories, that's not everything I want as an attacker. I want a worm that spreads all over the internet, but that's not the whole picture, because the Veracode repository has about 1.6K dependents. So I can also infect all of them and all of the repositories that depend on them and so on recursively. And the action zip repository also has about 600 dependents, but that's still not the full picture, because the Hangfire repository actually creates a nugget package that is being downloaded 9.4K times a day. Each day, it has about 10K downloads, which also, by infecting the Hangfire repository and hoping it will release its code as a package, as a nugget package, we can infect all of its users. But that is still not the whole picture of this attack. This is only public data we have. What about all the private repositories that are also depending on those repositories? Probably much, much, much more. And you probably think to yourself, okay, so that's a huge impact blast, that's crazy, amazing, but that's still not the representation of the real world. The real world looks something like this. I found many, many cases like this, much, much bigger attack trees, much more complicated, and I can tell you that I found very popular open sources that I was able to or directly compromise or indirectly by infecting their dependents. And also I found many, many huge companies that all of you probably use their products that are vulnerable to this attack, and I could execute code in their repositories and infect them by infecting the weakest link in the chain, basically, of repositories that they depend on, and so on. So this is the full scale of the attack itself. Now, let me show you and let me introduce to you the Dendro worm. The actual worm that implements this, I'll show you a short POC. The word dendro comes from the word dendrology, which is the science and study of woody plants. Now, let's get to the demo itself. Before we get to the demo, I'll show you a quick overview of what you're going to see. So we have this environment. We have a target repository on the left we want to attack. It has a CI/CD pipeline that uses the random action v1 tag. And it also has a CI/CD pipeline which uses the revdate action repository using a main branch reference. And the revdate action is a composite action which directly depends on the rev action repository. Now, as attackers, we start with the initial ability to push code to the repository. And what you'll see in the demo is that the attacker infects the repository with the worm code, which means instantly that the revdate action repository is compromised because it directly depends on the rev action repository. After that, we'll simulate a commit to the random action repository to trigger its CI/CD pipeline, in which our worm will run and it will try to override the v1 tag of the random action repository. And the v1 tag is used by the target repository, in which will also simulate a commit by the maintainer, which will trigger its CI/CD pipeline, and our worm will run on the CI/CD pipeline of the target repository and will be able to steal one of its secrets. So let's see the demo. Thank you. Okay, so we have the first repository. You can see a graph on the bottom right that shows you the progress of the attack. Here we infect the repository with malicious code. This is just a POC in Python. We can obviously make this code much more hidden. But this code downloads the malware, installs it, and executes it from a remote server. Okay, so now we see the second, wait, I'll just go back a bit. Okay, so we commit those changes, and we go to the second repository. We can see its action YAML that is directly using the action that we've just infected. So no need to do anything here. It directly uses it. Now we go to the third repository. We can see that all this action does is generate some random numbers. And we can look at its CI/CD workflow file, in which we see that it uses the second action. Another thing we can see in this repository is that it has a tag, which was created yesterday, a v1 tag, as you can see. Now we simulate a push by the maintainer to the repository to trigger the pipeline. This will trigger the GitHub Actions workflow. And now the malware will be downloaded from the server by the compromised action. And you'll be able to see on the server on the right, we see the download request. And you'll see that it also sent its GitHub token to the server on the right. And it overwrote the v1 tag of the repository. You can see now the tag is dated to now. And we can see its commit, which contains the worm code. Again, the download and execution of the worm. And now we are in the last repository, the target repository. We can see that it has a secret, and it uses the action repository that we've just infected its tag. And we'll again simulate a push to the commit by the maintainer. Push to the repo. And now the workflow will trigger, and you'll be able to see on the right that we've successfully stolen the secret and sent it to the server. Here's the download request. And you can see in the red box the secret that was stolen. Woo! Yeah. Okay, so that was the demo. That is an actual POC of the worm. I reported this issue to many organizations. I got some bounties. Most of the organizations I reported it to didn't consider it as an issue because it's an issue maybe in a dependency of a dependency of a dependency. Some of them recognized it, some of them not. But still, it's probably possible to execute this attack today on many repositories because of the interconnectability of the whole GitHub Actions ecosystem. Now, how can you protect yourselves? So you can set the GitHub token and any personal access token you use, and you can set the permissions to read. You can configure branch protection rules. You can use protected tags, limit outbound network connections from the runners to prevent download of malicious components, pin actions by using hash, and you can use also this repository by GitHub's security team. And you can also read, if you want to understand the attack more and get more details, I've published a blog on Palo Alto Network's website, which you can read more details and more examples about the worm itself. And that is everything today about GitHub Worms. Thank you.